All right, well, thanks everyone for joining. We are, let me, hold on. We're really excited to have Dr. John Dorelli with us today to present on some of their preliminary work using tracers to study the Nightside Auroral zone. So this is obviously something that's near and dear to our hearts here at Cinema. So we're really excited to hear John present some of his work along those lines of what they've learned that we can kind of take with us while we're doing our own studies here in Phase B. And before letting John kick off, we will be taking a little bit of a break in the next 2 months from our seminar series for July and August, but we'll pick back up in the fall with some other great talks there that we've already started to get lined up. So, John, why don't you take it away? We'll have some nice discussion after you're done.
Okay. Well, thank you so much. Thanks for the Cinema team for inviting me to talk about tracers. And I also want to acknowledge a few folks here, Rainer Friedel in particular, for really kind of pushing the idea of doing tracers back orbit science. The tracers back orbit, tracers is focused on the day-side magnetopause, but it's also possibly collecting high time resolution observations throughout its orbit. So there's a lot of opportunity to do night side stuff, for example. I also, on this list here, I want to specifically call out Daniel Da Silva, Dubien Du Sur, Ian Desjardins, and Natasha Buzelikova at Goddard. They are supported separately by Living with a Star Strategic Capabilities project, and they've been helping a lot with doing simulations of various kinds for tracers. And of course, the tracers team, Craig Kletzing, who is definitely with us in spirit, and I'm sure would be very happy to see the success of tracers just beginning its phase E now. Craig, as we know, passed away a few years ago and passed on the PI ship to in the very capable hands of David Miles, who has steered tracers successfully through many twists and turns to a successful beginning of phase E. And then, of course, the instrument teams. I love this video because you can actually see accurately where all of the instruments are on tracers. This is kind of the closest you can get to flying along with tracers. And so we've got thermal ions and electrons. We've got a two-dimensional electric field to measure the convection velocity, and two magnetometers on each of the spacecraft. David Miles is also the PI of the MAGIC instrument, which is kind of an experimental technology demonstration. And then we've got the MAG instrument in UCLA. So, it's a full comprehensive suite of plasma instruments with two spacecraft ready to do some very exciting science. Okay, and so let me see if I can, yes, good. So tracers is very similar to cinema in the sense that it is attempting to remotely from low Earth orbit observe global stuff. Tracers is focused on the day-side magnetopause, in particular the cusp precipitation, and cinema will be focused on the tail. But there are lots of similarities, it turns out, in the philosophy of these two missions. So Tracers has some specific science goals. These three that I've listed here. So with two spacecraft, so on the left, this is one of my favorite images from SDO. It's not a particularly exciting solar flare, but I love this because you can actually see the sort of textbook cartoon two-dimensional picture of reconnection happening just visually. And if you kind of see these two flux tubes are coming together and there's a little current sheet and then the plasma kind of flows out on both ends. And we don't really have the ability to do that in the magnetosphere. We know something similar is happening. There's kind of mountains of circumstantial evidence that something like this is happening. And now, for example, with MMS, we've been able to capture the sort of microphysical processes, but it's all local observations. We kind of have to use models to kind of build a global picture of this. But with two spacecraft in low Earth orbit, you can start to get at questions like disentangling spatial structure from temporal structure. And that's science objective 1, which is to determine whether reconnection is spatially variable or primarily temporally variable, or, are the structures seen by both spacecraft correlated or not correlated, that sort of thing. And then in cases where you have temporal variation, you can actually use the particle precipitation to estimate things like the local reconnection rate, or really the local electric field that is causing the magnetic field lines to convect over the magnetosphere. And the way this works is, imagine you're here at low Earth orbit and you're looking at precipitating ions coming from the reconnection site. The first thing you're going to see, because you have this, you have particles streaming down, but they're also convecting perpendicular to the field line. So the high energy particles are going to be seen first, and then increasingly lower energy particles because of the field line convection. So you see this energy latitude dispersion effect. And by measuring the slope of this low energy cutoff here, you can actually estimate the convection velocity of these field lines, which is basically a proxy for the local reconnection rate. So then you can determine how the reconnection rate in principle varies in time. And then the third science objective here is, I think, really Craig Kletzing's baby here. It's really you're determining temporal variations, how the temporal variations of reconnection propagate to the ionosphere, and how does that show up in the particle precipitation. So here we're talking about things like Alfvén waves propagating from the magnetopause to the ionosphere, and what do those look like? So I'm just going to spend a slide each for each of these objectives, and I'll go through these kind of quickly because I just said a lot of words about those in the previous slide. But how are we doing? So I think we need to be a little bit careful about terminology here. So how are we disentangling space and time? What is meant by temporal reconnection here is, so first of all, what you're seeing here in these particle spectra, see this staircase-like structure. These are called cusp ion steps. And one of the ways in the literature that, there are a couple models to explain these steps. Why do you see these kind of jumps in the precipitation superimposed on this overall energy latitude dispersion? One idea is that you've got temporally varying reconnection at the magnetopause, like flux transfer events or something like that. And the other idea, competing idea here, is that you have spatial structures. And so these field lines are just mapping to different spatial structures on the magnetopause that are separated in space. And if it's temporally varying, you expect that these steps should be kind of moving along with the field lines. So you would see, you do some correlation analysis between the two spacecraft, and if the steps are occurring at different latitudes, then these structures have moved along with the field line. If they're occurring at the same latitude, it's a spatial structure. Okay, and then for the second objective, we're trying to actually measure the rate of reconnection. And there's a couple ways that one can do this. You can do the kind of standard thing that I think most of us are familiar with, where if you can define some merging gap on the open-closed field line boundary and measure the plasma flow across that boundary relative to the motion of the open-closed boundary itself, that's a proxy for the reconnection rate. And then from the particle precipitation, you can look at the slope of the dispersion and get an independent measure of the reconnection rate that way. And so currently, the Tracers team is testing both of these methods using global simulations. And I'll show some of those results in this talk. Oh, and then the third objective, this goes all the way back, to really kind of ancient history in the 90s with sounding rockets. So Craig and Roy Torbert with sounding rockets saw what are called time dispersed electron structures. And this is happening on kind of millisecond time scales. something that can be seen for the first time with tracers with its tens of millisecond electron observations. And the thought here is that these things are accelerated by impulsively by inertial Alfvén waves. So if you imagine you have reconnection here, there's something wiggles the field line, and Alfvén wave propagates down. If the perpendicular scale of that wave approaches the electron inertial scale, and that can actually happen close in the auroral acceleration region, you can get very large paraelectric fields, and those can accelerate electrons. So that's something that tracers is really going to be able to accumulate a lot of these observations at high time resolution. Okay, so what is the tracers? I'll be using the term region of interest for tracers. So the science region of interest is basically we're trying to maximize the probability that we encounter the cusp. And the idea, and so this is modeling by Steve Petrinick, who's calculated the probability of encountering the cusp, and that feeds into the definition of this region of interest. So it's basically just a range of latitude where high time resolution observations are being taken. And then by back orbit, we mean basically everything else outside of that region of interest, where the processor on board is either averaging or decimating the data so that you're not accumulating high time resolution data. But if you could have more regions of interest, and Tracers is actually in the process of compiling a list of so-called non-cusp ROIs, you could get high time resolution very easily in other parts of the orbit. Okay, so I think it's probably widely known at this point that Tracers, one of the spacecraft, had a power anomaly. To make a long story short, that that spacecraft is operating only on solar power. And so that required, as you might imagine, a drastic change in the science operations, the concept of operations here. So originally, the region of interest was the northern cusp, and here's the back orbit, the rest of it. Now, just because of basically the time it takes to fire up all the instruments once the affected spacecraft is in sunlight, we basically have to wait for the southern cusp. So everything has been switched to the southern cusp. But the side effect of that, that's really great, is that the magnetic alignment of the spacecraft is now going to also be favorable in the Nightside auroral zone. So we can pick up conjunctions between the tracer spacecraft and ground assets, and as we'll see later, other spacecraft that are making observations in the Nightside auroral zone, like REAL, which was actually launched with tracers. So we'll show some exciting results from some of those conjunctions. And there's a big list of these conjunctions that's being compiled by the tracers team. So not only are we doing science in the back orbit, but we actually have additional ROIs where we're going to have high time resolution data in the Nightside auroral zone sooner rather than later in some extended mission. Okay, so now that we've kind of talked about the tracers' main science objectives, I want to move on to some of the less obvious ion dispersion signatures that one encounters, and I think this is where things start to get interesting. If you start to look at the bigger picture, you start to realize that tracers, in addition to answering those specific science objectives, can actually get a lot of information about the global structure of not just where the reconnection sites are, but current sheets in the magnetosphere in general. And so these things called overlapping ion dispersions, it's exactly what it says. If you have two dispersion events and they overlap. So there are several proposed explanations for this. One proposed by Fuselier et al. If one of the dispersions is associated with a reconnection event somewhere on the magnetopause, and you have another one overlapping, the simplest explanation, you've got multiple reconnection sites, and your particles just happen to be sampling both of those at the same observation point at LEO. Brandon Burkholder has recently done some simulations, global MHD simulations, where he's tracing particles in the electromagnetic field of the simulation and trying to reproduce these overlapping dispersions. And he's come up with a really interesting idea that if you kind of look at the histories of these particles, you get particles that have different histories within a complex flux rope structure, like a flux transfer event at the dayside magnetopause, and that can actually result in the particle at a given observation point, phase space density having this sort of multi-peak structure at different energies. And then a third explanation that I think I'd like to suggest, also from global MHD simulations and following guiding centers through the simulation, is maybe these are just telling you something about spatially separated current sheets that may or may not have anything to do with reconnection. So in general, if you have some global spatial structure of current sheet sources, that is going to show up locally as some velocity space structure. And so just mathematically, and I promise this is the only, I think this is the only math slide in here, but the cartoon picture here is that if you're observing particles precipitating at low Earth orbit, those particles have had histories where they encounter potentially multiple current sheets. And to model this, you can't just follow the guiding centers and pretend that these current sheets are sort of transparent. You actually have to somehow model the interaction of the guiding centers with the current sheets. And a very simple model for that is that you just have some scattering process, some effective scattering process, and there's an isotropization mechanism that is happening here. And this is where some of the similarities with cinema are becoming apparent because we know that if the current sheets are thin enough, guiding centers will scatter just because of the enhanced field line curvature, and that will be some kind of energy dependent scattering process. But if you model this very simply like this, you get what looks very much like kind of a radiation transport effect, where you have the thing that's interesting about this is not only do you have scattering and a loss of guiding center phase space density throughout these current sheets, but each of these current sheets becomes an independent source of guiding center phase space density. So it's like you have multiple sources contributing to the same observation point. And this is kind of like, spectroscopic analysis of radiation. We have multiple possibly overlapping sources. And one can imagine that, if you were smart enough, you could decode the multiple peaks in velocity space for many different observations and solve the inverse problem and then get some information about what the spatial distribution of the current sheets are, just like you do with regular spectroscopy when you're observing photons and trying to figure out something about the structure of the sources. Here's some initial modeling along those lines, and I want to actually call out Daniel De Silva's work at Goddard. So he really did a lot to advance our guiding center simulations by making them run on high performance computers in such a way that we can actually, in a very reasonable amount of time, produce energy time spectra for many different observation points at LEO by integrating guiding centers in global MHD simulations and then solving that radiation transport equation that I showed on the previous slide. And what we can do is we can actually track where all the current sheets are, excuse me, in the simulation. And then we can calculate the spectra and we can identify each of these overlapping ion dispersions with a separate structure on the magnetopause. So surprisingly, what turned out was that for southward IMF conditions, we do get the subsolar magnetopause, and that's kind of as expected. But we also get these cusp sources, which you don't necessarily expect under southward IMF conditions. This is pure southward IMF conditions. We still have a current sheet up here. And that's simply because the solar wind has to be deflected away from the magnetosphere, whether it's under southward conditions or under northward conditions. There's a current sheet sitting here over the cusp. That can actually be an independent source of ion precipitation and also electron precipitation. So that was very interesting. And Daniel, when we saw this in the simulation, Daniel went through DMSP data. This was before the launch of tracers. and found this event, which looks very similar, where you actually see these, what we were originally calling triple ion dispersion. But I think after, discussion with Stephen Fuselier and Karl Heinz Trattner, who are kind of experts in these things, what it really is more like is a double dispersion with possibly an ion step, a cusp ion step, as you can see in here, right? So you've got, these are well separated, the first two dispersions, but then the second pair looks more like a step. The key point here is that all of these overlapping dispersion signatures are coming from widely separated regions on the magnetopause and not necessarily reconnection. There could be subsolar reconnection producing this, but if you have a cusp current sheet and you have a convection electric field, you will get another ion dispersion associated with that. And so the other thing we saw in these simulations was we could pick up the electron dispersion, which is not something you could pick up with TMSP. And one of the things that we were predicting with tracers, because of the high time resolution electron observations, is that you pick up the electron dispersions, and that's exactly what you see. This, I think, is just amazing, an amazing results that with the ACE instrument on tracers, you can actually pick up, you can resolve these electron dispersions. And you see them in the correct, going in the correct direction, depending on whether you're in the northern hemisphere or the southern hemisphere. And then they've even been able to do some statistics with respect to the IMF clock angle to show that these are happening primarily under southern IMF conditions. You do see them at other clock angles, very, very small clock angles too, but it's predominantly a reconnection related effect. So it's not hugely surprising that we picked this up. It's kind of an amazing technical feat that you can see these and resolve these. But the interesting thing that's coming into play is that you see all of this other structure in the electrons, and it's often not highly correlated between the two spacecraft. So I think somewhere down the line we'll have to sort of decrease the separation of the satellites to kind of figure out what's going on with the electrons. But that will come after we've addressed the science objectives using the ion dispersion events. But there's a lot more to the story of the electrons. I think that's remaining to be told with tracers and dayside reconnection. Okay, so tracers focused on the dayside magnetopause. One might ask, what do these dispersion events look like globally? And so Tom Sortorellis has this really great paper where he's kind of looked at statistically all these spectra that have low energy cutoffs associated with them, and kind of mapped them in this kind of invariant latitude range defined with respect to particle signatures of boundaries of the poleward auroral boundary and the equatorward auroral boundary. So you kind of sort of map these particle boundaries into a single picture here, and you can pick out these really interesting patterns. And so this tells you that we haven't been able to do something similar with simulations until recently. What we're seeing, what I'm showing in the bottom here is guiding center simulations at many different magnetic local times, and some patterns actually start to show up. So, when you're crossing near noon, this is the triple dispersion, or but probably more appropriately called ion steps. This is kind of the standard thing that you would expect to see under southward IMF conditions. As you start to move away from noon, you start to kind of pick up these overlapping dispersions. So this would be sort of double dispersions, which are commonly observed by DMSP. But if you go further to the flanks, you start to get very complicated things, right? You're starting to actually pick up stuff from the night side in superposition with stuff from the day side. So these are more complex looking ion dispersion events, but I think they also give you global information about what's going on. And I'll show you a tracer's observation that really nicely illustrates this. So here's a tracer's observation of a complex ion dispersion event. And this is from Dibiendu Sur. This is a paper in preparation for the tracer special collection. What Dibiendu found for this November 7th ion dispersion event is that so Debian has developed some software to automatically track the low energy cutoff here at both spacecraft, and then do a cross correlation analysis of the low energy cutoff. And you can see here that these are really nicely on a large scale, on the scale of the whole event, correlated. And you can see the reversal of the dispersion here, right? It's forward and then it becomes reversed. But there's some variations on smaller timescales. Uh, so we wondered what is causing that. If you do a simulation of this, a global MHD simulation, and you trace the guiding centers, what you find is that along the tracer's trajectory, here's where the field lines are mapping. So this, if you can see my arrow, this near the subsolar magnetopause is the first field line along this tracer's trajectory. And then the field lines go along the flanks, and the tracer's trajectory just happens to nicely map along the dayside magnetopause. All the field lines are kind of uh, hitting the flank magnetopause. So you're covering a huge region of the flank here with this couple minute interval along the tracer's trajectory. So this is basically telling us this is why low Earth orbit observations are so great for capturing global information, because the field lines just map to widely separated regions. So all of the information about where these field lines are connecting to current sheets globally is captured in this very local observation of velocity space structure. So what we are suggesting here from the simulations is that this sort of forward dispersion is coming from subsolar magnetopause convection, and this is going sort of in the usual sense. By the way, this is I should mention this is northward IMF conditions with a very large earthward pointing BX. And I forgot to show that here, but it's a northward IMF case. So you would expect with a significant BY. So you would expect some combination of poleward of the cusp reconnection with a flow reversal, and then subsolar reconnection with the usual sense of the convection of the solar wind around the magnetosphere. And that's exactly what we see here in the simulations. This forward dispersion is mapping to subsolar magnetopause flow, and this reverse dispersion is mapping to cusp flow. And you can see that in these plots of X, Y, Z, GSE. The bottom three panels here, I'm showing the location in X, Y, Z of the most intense current sheet encountered by the guiding center. And so you can see, particularly in this bottom plot, you can see that the two cusps here where the reverse dispersion is happening are on opposite sides in Z, right? So you're picking up both cusps with this southern hemisphere tracer's trajectory. There are some differences that are interesting. The cusps that we're seeing in tracers have a much steeper slope than the ones we're seeing in the simulations. And I think that's not terribly surprising, because the current sheets in the MHD simulation are this is basically resistive MHD. So you have a very different current sheet structure locally. It might be more spread out than it is in reality if reconnection is happening on a more kinetic scale. So that's something for future work. But it's kind of amazing that we're able to recover qualitatively this very complex event. Okay, so moving on now to the Magnetotail. I really like this figure from Fukushini et al. In the 90s because it's really kind of it's really giving us information. It's giving us a global picture of the Magnetotail. And while all of these different precipitation structures, sorry, this thing is automatically moving forward, unfortunately. It looks very complex, but there are patterns that emerge. And so you see things like broadband electron precipitation, the polar rain, and you can see this upper cutoff of the polar rain that has a slope here that's very similar to the ion precipitation that is thought to be associated with reconnection in the tail. That kind of indicates that this might be the location of the open-closed boundary where reconnection deep in the tail, I'm just going to go on to this, is happening. And so if we do a similar kind of simulation in the Magnetotail, Sorry, we can pick up all of these current sheets, and we can show by tracking these particles and where they encounter the current sheets, where the velocity dispersed ion structures are mapping to. And it turns out these are mapping to way down the tail, maybe 50 to 100 RE down the tail. But we're also picking up current sheets much closer to Earth. And you can see here, here's sort of near the dipole transition region. That's mapping to dispersive structures that are much closer, much lower latitude. And so the neat thing about this is you can see that at any given observation point, here, I can pick up multiple peaks in the ion flux that are mapping to widely separated regions in the magnetotail. So if we were just clever enough to kind of solve the inverse problem, we can use this low Earth orbit data to recover or give us information about the global structure of the entire magnetotail. Okay, and so I wish it were that simple, but what happens, so this simple guiding center approach where you're following guiding centers in the electromagnetic fields, and it's just kind of a ballistic guiding center process where there's really no processing of the guiding center en route from the current sheet to low Earth orbit. That's actually not how things really work. So this broadband electron precipitation, usually referred to as the Alphanic aurora, is thought to be associated with a turbulent cascade in the auroral acceleration region. And this was pointed out by Chaston back in 2008 using fast data. You can actually calculate the power spectral density of the magnetic field. You get a nice Kolmogorov spectrum here in the inertial range. And then at kinetic scales, the spectrum actually steepens, right? This indicates some kind of collisionless dissipation process for the turbulence. But the neat thing is this is where you see these turbulent fluctuations is where you tend to see this broadband Alphanic aurora. So there, what is the relationship there? How is how is this turbulence driven? How does it accelerate the electrons? What's the dissipation mechanism here? So one clue to this is, if you look at how Alphane waves are generated by reconnection in the magnetotail, I'm going to go back to here. If you have a current sheet that's forming in the magnetotail, the electrons that are carrying that current are bending the magnetic field out of the plane, and that's producing field-aligned currents that you don't pick up with regular MHD simulation. And this was pointed out a long time ago using PIC simulations of reconnection, that these structures along the magnetic separatrices of field-aligned currents could actually map all the way down to the ionosphere. And so here's just a very simple simulation I did using what's called the reduced MHD model. And so reduced MHD, I lied actually before. There's more math here. I'm sorry. So what this is imagine if you have an Alphane wave propagating from the magnetotail down to the ionosphere. When you get to the auroral acceleration region, you're in a regime where you have a very large background magnetic field, and the perturbations of the magnetic field perpendicular to that magnetic field are small. And so you can you have these widely separated timescales where you might have slow variations perpendicular to the magnetic field that are sort of plasma convecting perpendicular to the magnetic field being carried by the Alphane wave. But then the Alphane wave itself propagates along the magnetic field direction very rapidly. So when you have these widely separated timescales, you can actually do a dramatically reduced model of MHD that is much less computationally expensive than if you would try to solve the full MHD equations in the auroral acceleration region. But if you do that, and what I'm showing on the left here is if I just take that field-aligned current pattern from the tail reconnection, and I impose it on at the top of the auroral acceleration region, and this I think is at around 2 Earth radii. And we're looking down here on a spherical shell between, in a range of latitudes corresponding to the acceleration region, and just imposing this field aligned current pattern there. Because that field aligned current pattern has a vorticity associated with it, and this is usually something that's neglected in MHD simulations. We map the field aligned current, but we don't consider the corresponding vorticity pattern that has to be carried by that field aligned current by the Alfvén wave. If you do that, then you can drive all kinds of interesting dynamics in the auroral acceleration region here. And so I take this with a grain of salt, because this is very much a cartoon level simulation where I've just kind of imposed this arbitrary field aligned current structure and then just kind of let it rip without any kind of magnetosphere dynamics constraining anything. But it's basically just to show how easy it is if you have a field aligned current that's being imposed at the sort of inner boundary of an MHD simulation to drive turbulence in the auroral acceleration region. And all of this fine scale structure in the field aligned current that develops as a result of that. Okay, and I want to also plug some results from Huang et al., who was doing some work at Dartmouth with Yixin Liu. Yixin and Huang have argued that some of the structure, some of the discrete aurora structure that we see, in particular these rolled up vortices, could have something to do with reconnection occurring in the auroral acceleration zone. So I think their idea was that maybe these discrete auroral arcs are associated with current sheets that can become unstable to secondary islands, and then those things can then get rolled up into what look like these auroral structures that we often see in the observations. That doesn't really tell you how the current sheets form. I think a model like the one on the left, where you have some large scale current structure, field line current structure coming in and rolling up into all of this fine scale structure, we know that there's an intimate relationship here between the turbulent cascade and reconnection. So one of the dissipation mechanisms of turbulence is possibly reconnection. You form these coherent structures here, and then they merge and dissipate magnetic energy by reconnection. Certainly, that's possible in the auroral acceleration zone, and that was something that was new to me and I hadn't appreciated before reading the work of Huang and Yixin Liu, and then looking into these reduced MHD simulations driven by field aligned currents from the magnetosphere. So there's another possible dissipation mechanism. If you look in the literature on turbulent dissipation, you'll find that people kind of fall into a couple of camps. There are the coherent structure reconnection folks that think reconnection is playing the dominant role in turbulent dissipation. And then there's wave particle interactions. And usually this is framed in terms of Landau damping of inertial Alfvén waves or kinetic Alfvén waves. But what Craig Klutzing was doing back in the 90s is something really inherently different, which is looking at a highly nonlinear interaction between an inertial Alfvén wave parallel electric field structure and the electrons, right? And so you get this really interesting nonlinear interaction between the wave packet and the electrons that Craig was arguing explains some of these time dispersed structures that one sees in the Alfvénic aurora. And so Ian, has developed a really nice drift kinetic model of this. What Craig was doing back in the 90s was not really self-consistent. It was just some prescribed paraelectric field and then see what the particles are doing. Ian has been working on making it a self-consistent paraelectric field so that you can self-consistently study the nonlinear wave particle interaction. And it turns out that you can catch a lot of these things even in the dayside ROI with tracers, because some of the field lines in the cusp ROI are actually mapping deep into the tail. So you can actually pick up some of these inverted Vs. And often, and this was also new to me, I didn't appreciate the fact that often when you see an inverted V like this, you can actually pick up all of these broadband electron precipitation time dispersed structures kind of raining down from the inverted V. So that kind of suggests that there's some relationship between inverted Vs and the Alfvénic aurora, but there's not really much in the literature on this question, other than just noting that these things sometimes are associated. And so the puzzle is, what is the relationship between inverted Vs and this alphanic aurora? The nice thing about ACE is you can now resolve these with tens of milliseconds. So this event here is blown up here. You can see each of these individual things. And what Ian has shown with his simulations is that these time dispersed structures actually seem to be an accelerated ionospheric population, which is secondary electrons coming from the primary inverted V, right? So you have this inverted V stuff coming down. You have secondary electrons that are produced that are basically a superthermal tail from the perspective of the ionosphere. Those things come up and probably bounce back and forth between in the electric field that's accelerating the inverted V. And every time they interact with that potential, they get time dispersed, accelerated. So that's a very interesting, possible explanation for the relationship between an inverted V structure and these time dispersed structures. And then I just want to, before I go into, the tracer's real conjunctions, I just want to point out that in this reduced MHD model of turbulence, a kind of interesting picture emerges where if you have a large scale, Alfvén wave field aligned current pattern propagating to the ionosphere, that can generate turbulence, and you'll get a whole cascade. That cascade will go all the way down to the inertial scale. And once you get down to the inertial scale, then you have inertial Alfvén waves, and the kind that Ian was modeling. And you get large parallel fields associated with that, in addition to any kind of reconnection electric fields that you might get. And so, there could be a natural relationship between field aligned current structures associated with inverted Vs, turbulence, and inertial Alfvén wave structures associated with the alphanic aurora. All of these things could really be sort of coupled together into some overall picture with different timescales. And so that's something that I think tracers and later cinema is really going to be able to get to the bottom of with multi-point measurements. Okay, and so what about the conjunctions? All right, so we have this is courtesy of David Miles, and David and the real team have been looking at these conjunctions between tracers and real and all sky imagers. And this, I think, is the slide that was most interesting to me, because you see an example here where there's some overlap between the real particle observations and tracers. And some of the time you can actually sort of map the inverted Vs that are seen by tracers to the ones that are seen by real. But there's this interesting gap here where tracers follows behind real by 23 seconds, and real did not see anything, but then tracer sees this kind of really brilliant region of inverted V and associated alphanic aurora. And this is 23 seconds apart, right? So what is going on there? Is there some kind of process whereby this inverted V is forming along with the alphanic time dispersed structures? So I think there's a lot to be done here with these conjunctions on the Nightside Auroral zone to really understand the origin of inverted Vs and the relationship to alphanic aurora, and kind of pin down the timescales involved for these things. And also with the two tracer spacecraft, like I said, there's some dayside ROIs where both spacecraft are actually seeing field lines that map to the Magnetotail, and you can pick up multi-point measurements of inverted Vs and alphanic aurora that way as well. So a lot of exciting stuff to be done here. Looking back to how tracers can inform cinema, I am not the expert here on the isotropy boundary, but as I was reading about it and kind of trying to connect it to some of the work that we're doing relating much lower energy particle precipitation to current sheet structure, it occurred to me that we're we may be talking about the same thing, right? But at different energy ranges, right? So tracers is sensitive to very thin current sheets, in its energy range of, say 10 eV to tens of keV. That would be way out here. And cinema covers will cover the full energy range. So you can sort of pick up, these isotropy boundaries, well into the dipole transition region here. Tracers will, provide a very similar method of remote sensing magnetotail structure by relating precipitating flux to current sheet structure. So I think there's a lot that we can do to make progress on that problem in preparation for cinema. And so I just took the liberty of, writing down a few, science questions here. Tracers, like cinema is going to be making these, several minute exposure snapshots of the whole magnetotail every 90 minutes. And so you're going to get a lot of these, thousands of these events over the course of the mission. And so we can start addressing some of these questions that were raised in the previous slides here. So how does the global configuration of the tail evolve in response to solar wind conditions? I think cinema is basically addressing that question in the tail by looking at the global structure of the current sheets, prior to substorms and how that's related to solar wind conditions. Another thing that I think would be interesting and has not really been explored a whole lot is what is the relationship between these velocity dispersed ion structures, which are the sort of ion dispersion events for tail reconnection, and magnetotail reconnection. Where does the reconnection happen? The simulations seem to indicate that it happens very far down the tail. But then there's this gap between the deep tail reconnection and the sort of substorm related stuff that happens closer to Earth. What can tracers tell us about that? What is the relationship between particle precipitation and field aligned currents under different solar wind conditions? So, we know that the particle precipitation is not just passive guiding centers coming in from the magnetosphere to the ionosphere. There are field-aligned currents carried by Alfvén waves associated with those as well. So understanding how those field-aligned currents interact with the particles is important for understanding, electron acceleration, the auroral acceleration region, the Alfvénic aurora. And then finally, how is Alfvén wave energy coupled to the ionosphere in the Nightside auroral zone? I think we are doing pretty well on time, and I thank you for your attention. And I think we probably have plenty of time for questions.
Yes, perfect timing, John. Thank you so much. Virtual round of applause and in the room. Plenty of time for questions. Please feel free to raise your hand if you have any, or put them into the chat and we can read them out. Bob Lysak, why don't you unmute next?
Hi, great stuff, John, and kudos to all the Tracers team. I thought you might be interested to note that this event that you showed for me in Desjardins of the inverted V sort of going broadband near the peak is something that we've been observing with the Juno satellite at Jupiter. And we've been interpreting this in terms of the fact that it turns out at that point, the inverted V, that image right there, that inverted V for our parameters at least has gone unstable to the excitation of inertial Alfvén waves at that point.
Oh, nice.
And so there's I'm excited to see this happening in the Earth's magnetosphere as well. So great stuff. Thanks.
That's interesting. I wasn't really aware of the Juno observation. So you're saying the inverted V current, the current sheet is going unstable, and do you know what the mechanism of instability is, or
it's the electron beam itself is Landau resonant with the inertial Alfvén waves, and of course clearly if you just look at that spectrogram, it looks like there's very likely a positive slope in the distribution that can excite the waves at the Landau resonance.
Okay, that's interesting.
Yeah, we have a paper that's almost ready to be published in Science Advances. Ali Suleiman is the main author.
Okay. All right. So this is basically you have some pre-existing kind of soup of Alfvén, inertial Alfvén waves there, and the inverted V kind of interacts with them in such a way that these perturbations become unstable.
Yeah, yeah,
Okay, thank you. Yeah, that's something I think I'll put on Ian's radar to look at with his code.
yeah. I haven't seen that paper yet, but Ian, if you could send me a copy or a link to that, that'd be appreciated.
Sure. Yeah, it's currently in press, but I think it should be out pretty soon, and I'll definitely send you. I can ask Ian to send you a preprint as well.
Great, thanks.
Great. Yeah, and I think David Savit put a question in the chat that assuming there's funding, how long can the TRACERS mission continue to make science observations? How long can it continue?
Yeah, that's a very good question. There's multiple layers to the answer to that question, right? So, there are two spacecraft, and one of the spacecraft is really running on borrowed time, in the sense that it's being highly stressed. It's in this, it only operates in sunlight, and it's kind of a miracle that the team has, really made a heroic effort on the operations side and the science side to get it in a more or less nominal state. Every day that it continues to operate, everybody's like, wow, this is kind of amazing. And all the instruments are operating. So as long as that continues, then, there's one time scale there. How long does that spacecraft last? The other time scale is, more programmatic, which is, what do extended missions look like these days? And that's sort of a bit amorphous. So Tracers has been able to, even after this long commissioning period to recover SV1, it has been extended for Phase E through March, end of March, and then we'll, figure out, hopefully there will be an extended mission and there'll be an out of phase senior review associated with that. But we hope that we'll be able to start to torque to some of this more general science like Nightside or Auroral Zone, and other things for an extended mission, as long as the spacecraft are operating. And then, so the third layer of this is SV2 doesn't have any issues, right? So it's operating nominally throughout the entire orbit. And in conjunction with other low Earth orbit observations and ground assets, like REAL, for example, that we just showed, can do some great science on some of these topics indefinitely. Yeah, there are sort of those three timescales involved in the long-term science output of tracers, and I hope that answered the question.
Yeah, thanks, John. I think Robin had the next question, and then Tom will go to you after that.
Yeah, just a comment and question. The comment is just REAL has the higher energy particles, up to 2 MeV or so. So I'm really hoping we'll be able to find some nice conjunctions where, tracers provides those very low energy particles, and then REAL is providing the higher energy particles, sort of simulating what cinema might do. There is a gap kind of between 10 keV and 80 keV but that cinema will fill in. But and then my question was, could you just say a little bit more about the reconnect? You're determining the reconnection rate by the flow across the open closed boundary, I think. I mean, I'm familiar with using the size of the polar cap or using like the Newell coupling parameter with the where the open closed boundary is, but I'm just wondering if you've compared that with that Newell coupling or anything.
Yeah, so no, we haven't like compared that with Newell coupling or coupling functions or anything like that. But and the basic idea of this is, if you look at the open closed polar cap boundary, that is mapping to the X line. Some region of this open closed boundary, which is sort of this this gap region here, this merging gap region, is mapping to the global dayside magnetopause X line. So, and if you do the, if you do the math, if you calculate the line integral of the electric field along that dayside magnetopause X line, you can prove that is equal to the convection electric field integrated over the open-closed boundary. And so to measure that convection electric field, you have to keep track of the motion of the boundary, and you have to keep track of the flow across the boundary. And so we can keep track of both of those things. So we can, with ACE, we can, and those electron edges that I was showing you, those dispersion events, that's basically a very precise measurement of the open-closed boundary. And so with two spacecraft, you can track the motion of the boundary. And then the perpendicular electric field measurements are giving you the convection velocity. So that's how we're using the tracers observations to measure that.
Okay, but you have the electric field. That's right. Which we won't have on cinema. What is just? Can you remind me what the time resolution of ACEs and what kind of resolution you need to see those, see that
Yeah, it's like
dispersion in the open closed boundary?
tens of milliseconds resolution for ACE.
Oh.
And then, which explains why you can see those and you didn't see them on DMSP with 1 or 2 second resolution.
Yeah, I think it'll be kind of marginal for cinema, but I'm curious to hear what Tom says, so maybe we can let him.
Go for it, Tom. Why don't you take it away?
Okay. Sorry I didn't catch what Robin just said because I was looking up a paper I wanted to mention to John. Patnell had a paper in 2012 that made the case from DMSP conjunctions that saw the broadband aurora evolve into monoenergetic.
I think
that might be something that might be worth exploring with tracers with their, rather than just chance encounters and DMSP's 1 second observations.
I think Ian was telling me about that paper, if I remember correctly, and thinking along exactly the same lines of can we find more of these tracers events so that we can pin this down more, because it does certainly appear that way sometimes that the inverted V forms and the alphanic aurora seems to be kind of the initial stage of that. So we've been thinking about the physics of that and why that should be. We're not to veer too much, but we're kind of thinking in terms of what drives an inverted V from the magnetosphere. You've got some field aligned current source that comes in as an Alfvén wave. All of that comes in as an Alfvén wave. And then, the Knight relation would just say, okay, you've got field aligned current, so you need a paraelectric field. That's sort of the very simplified cartoon picture of an inverted V is get this kind of static process. But really, it's an Alfvén wave, and so you get a vorticity and you get turbulence associated with that. And what I showed was how easy it is to generate that turbulence and get a cascade. So, and that happens on some time scale, which is not minutes and hours. It's pretty fast, that cascade. So you can easily get to inertial Alfvén wave scales just after you form the inverted V. As you start informing the inverted V, you've got a turbulent cascade that's producing inertial Alfvén wave structures, and then those will then through various mechanisms. Bob was mentioning instability. You can very easily then get these time dispersed structures raining down. But then there's a decay process of that turbulence. And you can see that in the simulations I showed, where all of that stuff goes away and you end up with these static current sheets that would probably also be inverted Vs. So it's not, terribly surprising that you would have this relationship. There's good theoretical reasons for why you have this relationship. But yeah, the observations are kind of spare. So it'd be great to get many more of these observations so we can pin down these timescales.
Additionally, a second question, or comment, and I had a 99 paper where I tried to find the downtail distance to the reconnection sites, and I got distances between 30 and 80 RE downtail. with a very small number of events because of limitations of the DMSP observation. So I'm really looking forward to seeing what tracers can do with their higher quality, not to mention more than one spacecraft observations.
Yeah, yeah, as you know, I'm familiar with that paper, and
Mhm.
as I was, reviewing the literature and becoming familiar with all of these observations, it was really fascinating to me that the folks that were looking at velocity dispersed ion structures were putting reconnection way far down the tail. And other observations that are closer in, Geotail and, and Themis and MMS was really designed to look for reconnection at about 20 to 25 RE down the tail. That's sort of the canonical place that people think it happens. Why that disconnect? And I think if you look at global simulations, like I'm showing here on this slide, it's quite clear that there are two locations in the tail generally where reconnection is happening, one further down the tail and one closer in, particularly during substorm periods. And then there's a gap in between those where you don't see much precipitation. And this is also a well-known thing, as you know, this gap in the precipitation between the VDIS and the plasma sheet, the near Earth plasma sheet. One possible explanation is that you just have these widely separated reconnection processes. And why that separation occurs, I think, is a question that needs to be addressed. I don't think there's a great answer for why it looks like this generically.
I look forward to you having better quality observations so we can see the full distribution. I know that we saw in cases where we didn't have the convection speeds, so we couldn't look down, we found some very bright VDISs and some very dim ones. And you might get the feeling that the bright ones might be from the nearer, brighter source you're talking about, and the dimmer ones might be from farther away. But it'd be nice to see that actually shown. And Robin, was your question about our real data level 2?
No, I was asking basically trying to figure out what time resolution would be needed to be able to see that the slope and to resolve the slope and the electrons at the open closed boundary.
Oh, yeah, that's if you look at DMSP, Shara had a paper on this in 97. It's about, you can see it at the lower energies, the dispersion over maybe 2 or 3 seconds, sometimes more, sometimes less. And we don't see a slope at all at the higher energies in the polar rain because those electrons are going faster. So definitely sub-second. And I think, John, didn't you show some the slope with your higher resolution?
Yeah, I was just trying to ask
Yeah,
what
so
the ACE.
the polar rain, yeah, I mean, I think we're maybe talking about a couple of different things. Like, so the polar rain dispersion at the upper energies kind of slopes down with a slope that's comparable to the ion dispersion slope. But these dispersions that we're talking about in the cusp are much sharper, just because the time of flight of the electrons is so much shorter from the cusp from the day side magnetopods to the ionosphere.
I see.
And
Robin, were you
so,
talking about, I'm sorry, were you
I
talking
was
about
actually talking about the open closed boundary and
the polar rain?
right, but this I think we probably won't be able to see with cinema because I don't think we'll have enough time resolution to resolve these things that Jasper's been looking at because
Right.
these are much sharper.
We're looking at hitting 100 milliseconds with the ESA. That will
Oh.
be going at shorter time scales with the solid state telescopes.
Okay, that's better than I thought. I guess our requirement is a half second, but we'll do better.
We're planning on it right now.
Okay, cool.
Yeah. I'm gonna jump in. Sorry to cut this off. We're about to get kicked out any second here, but I thought there's one question in the chat that I thought would be really good to end on, and it's there's a question on data availability, which I think Ian and Robin addressed, but Mohammed asked, what are the opportunities you see for outside collaborators to use tracers data to address some of the broader questions you mentioned towards the end of your talk?
yeah, so tracers, has some data starting to become publicly available, and there's a requirement, to have level 2 files, within a certain period of time, a couple of months, few months. I would say, Tracers welcomes collaboration from the external community. I think the last Tracer Science meeting, was open to external collaborators. And I'll have to say the Science Operations Center in Iowa, they're a lot, they're making a lot of progress in making tools for analysis of the data and making things available to the public openly. So these tools are going to be ending up on open GitHub repositories for people external to come in and play with. So yeah, there's very much a desire to invite the community in to help look at the data. And we'll talk offline about how to, logistically how to do that, how to get access to the publicly available data. And also feel free to contact David Miles and other instrument leads on the Tracers team if you're interested.
Great. Well, let's all thank John again for another wonderful talk and for letting us hear about Tracers.
All right, thanks. And I very much appreciate the opportunity and looking forward to further collaborations with Real and helping to inform the development of cinema. So thanks a lot. Appreciate it.
Yeah, thanks. And so we'll just to reiterate, we'll take a quick brief hiatus in the next 2 months, and we'll pick up our seminar series back in September. So hopefully we'll see many of you at GEM and other conferences throughout the summer, and hope you guys have a nice time in the nice weather. So bye, everyone.